Okay, so in the in the previous lecture we had discussed about open and closed sets, right? In the topology. So we will be discussing about continuous functions in this lecture. About continuous functions. Okay. Before moving on to continuous functions, let us just briefly get into what is called the basis for a topology. So, what is basis for a topology? Okay. I won't get into much details of this, but I'll just rather give the definition and an intuitive approach to what it is basically. So suppose X is a set. Okay, let X is a set. Um, is a set. A basis for a topology on X, say B, or rather write it as this B. So it's a collection. It is a collection of subsets of X. It's a collection of subsets of X such that, so the property is obeyed by is that if you choose any element from X, for all elements small x in capital X, we will get an element from this B, let this be beta, or let me just write it as alphabetical B. I don't exactly remember how this notation is, pronounced. Okay, so there will exist an element, a basis element B, let's say, a basis element B, such that X is inside this basis element. And number two is that if you choose any element from the intersection of two basis elements, okay, let X be in B1 intersection B2, where both are basis elements. That B1 and B2 are both basis elements. Then you will get a third basis element, the third subset of X, such that X is inside B3 and B3 is completely contained inside B1 and B2. Subset of B1 and B2. So in this case, we say that this set, let's say it's capital B, let's say. So it's called a basis for a certain topology in X. So it's obviously relevant to the topology on X. So let me just give the relation between a basis and a topology. So a topology, say tau, is said to be generated. So it's said to be generated by B, by a basis capital B, such that, sorry, if and only if for all elements u from tau, so if you choose a, or rather I should say it like this. So topology tau on a space X is said to be generated by a basis B if and only if, a subset of X, say U, is open is open, that is it's inside tau, if and only if whichever element you choose from U. Okay, so for all elements X in U, there exists a basis element B such that X is inside this basis element and the basis element is completely contained inside U. Okay, that's the uh, that's the concept of a topology generated by the basis B. A simple diagrammatic representation of how a basis works is as follows. So suppose you consider the topology, the standard topology on R2. Okay. So previously in this discussion on closed and open sets, we had said that the standard topology on R is simply generated by the set of all open intervals in R. Right. So in that case, we can obviously refer to this fact that the open intervals in R forms a basis for the topology. let me first explain one short thing about basis. It will make it more clear. So if X, let me just state it as a lemma. This will have your intuitions clear about basis or the word generated. Let X be a set. Let X be a topological space. So X is a topological space. Let X be a topological space, and let X be a topological space with topology tau. Okay, and let capital B be the basis for tau. That is the basis which generates tau. Okay. Then tau is the collection of all unions of the basis elements, unions of elements in B. Unions of elements in B. Okay. That's the precise intuition. So basically, if you choose the elements from B, you keep on having their unions, you will completely construct tau. And that is what we had said in the discussions on open and closed sets, right? We had discussed that the standard topology on R, the standard topology on R is typically the unions, the all possible unions of the open intervals in R, right? Right. So yeah, so a short proof of this is as follows. So suppose tau is a topology. So let tau be the topology generated by B. Now we have already seen that, if you consider a collection of elements from capital B, then they are elements of tau, right? Because what do you have by the definition? We have definition that if you choose any element from an so if you consider an open set, that if you consider an element from tau, then every element of tau is such that it is contained in some basis element, and the basis element is indeed contained in the open set, right? So if it's a subset of an open set, that means it's contained in tau. So this typically means that this basis element will be contained in tau, right? So that means if you consider any collection of elements from this basis set, then the elements are contained in tau as well. So any collection of elements from tau, sorry, elements from capital B are in tau, right? Hence they are open. Hence open. Which implies their union. Which implies their union is also open. Union is open. Right. So therefore it's in tau, obviously. Or also we can directly claim the fact from here itself that their union is in tau, because tau is closed under arbitrary union, right? So therefore, if you choose the union of the elements B, where B are elements from the basis set, then this is obviously contained in tau. So the other way around, just if you prove the other way around inclusion, then we are done. And that's also quite easy, because let us choose a basis element from tau. So let U be in tau. Then for all x in U, there exists a basis element Bx, which is B depending on x, such that x is in Bx and Bx is contained in U. So that implies U is nothing but the union of all these basis elements, x ranging over all the elements in U, right? Therefore, so this basically implies that this U, so it's actually contained in the collection of all possible unions of the basis elements, right? So that actually tells us the fact that implies, so tau is a subset of the all possible unions of the basis elements, right? And so that implies tau must be equal to the union of the basis elements, right? So the topology generated by a basis is simply constructed by considering all possible unions of basis elements. So very usual example. So we know that in case of R2, right? We know that in case of R2, we consider these open balls, right? So U, X, R, we consider where these are the collection of elements Y from R2 such that the distance between X and Y is less than R, right? So they construct balls with center at X and radius R, right? Because since I am considering the standard topology, I will obviously consider D to be the standard Euclidean metric, right? It's the standard Euclidean metric. Standard Euclidean metric in the sense that if X is considered as the coordinate x1, x2, Y is considered as the coordinate y1, y2, then the distance function is given as this. So d of xy is nothing but the distance formula simply from x to y. So it's x1 minus y1 whole squared plus x2 minus y2 whole squared and the root over. So we know that this is the equation for a disk, right? Open disk. Right? So we have all these points in all these parts except the circumference. Okay, so this obviously forms an open set. This is a standard result on metric spaces. The open balls are open sets. These are open sets. So the collection of our open sets form a basis of R2 with respect to the standard topology. Let me just give a diagrammatic viewpoint of it. I'm not going to write the statement of the claim. Let me just give a diagrammatic viewpoint, because the diagrammatic viewpoint will obviously help you frame the statements of the claim. So what will be two arbitrary elements from? See, the first condition for a basis is obvious, right? Because if you choose any element from R, then obviously you can form a. Sorry, if you choose any, if you choose any element from R, you can obviously simply form an open ball, right? With a radius, certain positive radius R around that point. So that will be obviously an open set, or rather a basis element. So first point is very obvious. What I'm trying to say is that if this contains all open balls of elements in R2, okay, then if you choose an element from R2, you can obviously construct, then for some R greater than 0, you can construct the open ball, and X will obviously be in it because X acts as a center. What is the distance between X and X? It's obviously 0. So it's obviously less than R, right? Because R is positive. So that's obvious, right? So it's X and R. Yeah, right. So the first point is pretty obvious. The second point you can just obviously consider from this diagrammatic viewpoint. Suppose you choose two open balls. Suppose this is one open ball, and let's say this is one open ball. Then this gives you the open ball in the intersection. Obviously, the second point is valid if there is a non-empty intersection, right? If you consider two basis elements which do not intersect, then there's nothing to do about the second observation. Whatever we have in the second observation is when they intersect. So if you take two intersecting open balls, then their intersection contains. So if you consider this point in their intersection, suppose this is the B1 ball, this is the B2 ball, and you consider a point X from their intersection, then you can get this B3 ball, which contains that point X, and it's contained in the balls P1 and B2. So second point is obvious. Let's frame up this question, this very statement. Yeah, so I guess it's obvious. There is one very immediate definition in relevance to basis, which is a subbasis. Like we always have a habit to construct, a smaller space of something which we have already constructed. Like in case of a group, we have a subgroup. In case of a ring, we have a subring. In case of a field, we have a subfield. In case of a vector space, we have a subspace, right? So in case of a topological space, we had also studied what is the subspace topology, right? So it's quite obvious. So if you have a definition of a basis, then what the concept of a subbasis? So let me just give the brief That's sort of a definition, the concept of a subbasis. So basically, subbasis of a topology, it actually helps us construct the basis for the topology. Sort of that. So a subbasis for a topology, let's say tau on X, is a collection of subsets of X whose union equals X. Moreover, this is not that valid a point. The most valid point is that the topology tau is the collection of unions of finite intersections of the subbasis elements. Now we know that a topology generated by a basis is the collection of the unions of the basis element. That's quite trivial from this definition, that the basis for a topology, provided you have a subbasis, is simply the finite intersections of the subbasis elements, right? That is, suppose S is a subbasis, S is a subbasis, okay? So then the basis with respect to S, say B, contains elements of the form. So every element from B is a finite intersection, its size equals to 1 to n Si, such that each of these Si's are in capitals. That's right. So the topology tau is basically, so it's considering the elements over the unions over the intersections of these Si's, such that Si is X. That's the very obvious representation, right? Indeed, this forms a basis element, because if you have two basis elements, then both are finite intersections. So their union is also a finite intersection, right? Sorry, their intersection is also a finite intersection. Okay. So this is a standard definition for a subbasis. Let us not move into a deeper discussion. If we require any specific thing from the concept of basis, we will discuss it while studying the continuous functions. Okay. Let's introduce the concept of a continuous function at this moment. Continuous functions. Definition. Let x and y be continuous functions. Sorry, X and y are, let x and y be topological spaces. So x and y are topological spaces, and let f from x to y be a mapping. Then f is said to be continuous. If the inverse image of open sets in Y are open in X. That is, for all open sets. So if you choose an open set V from Y, then the inverse image of V is open in X. Okay, is open in X. That's the precise definition. Clear? So it's quite obvious, because since we are dealing with open sets when we are defining continuous functions, so the continuity of a function between two topological spaces is completely dependent on their topological structures, right? Because we know that the topological structure is what the precise definition of the term open sets, because the topology is the collection of open sets, to be very very lame. Okay, so so the definition of a continuous function is completely dependent on the concept of open sets. Hence, it varies according to the topology or the topological structure defined on its domain and codomain space. Is it clear? Now, one thing to be very, let us just come through certain observations. Certain observations, let's say, so f let f from x to y be a mapping. Okay, let f from x to y be a mapping, and let tau y be the topology on y. Be the topology on y. Suppose it has a basis, okay, generated by a basis by. Then for all elements u, or let's say v, for all elements v in tau y, then v is union of some basis elements, right? So it's unions of some b alpha. Alpha is in some indexing set lambda, such that b alpha comes from the basis by for all alpha in the indexing set lambda. But what is f inverse v then? So f inverse v is simply the union of the f inverse of each of these b alphas, right? So it's union over alpha in lambda, f inverse of b alphas, right? Now, since arbitrary union of open sets is open, therefore it's enough, right? It's enough to show that the inverse image of each basis element is open. Of each basis element is open to claim the function is continuous, right? I guess it's pretty trivial to observe, because if each basis element is open, that is, if f inverse b alpha is open, then their union over an arbitrary indexing set, this is also open, right? But if this is open, then that implies f inverse v is open. If f inverse v is open, then that implies f is continuous. So it's quite obvious, right? Is it clear? Similarly, a similar observation, if I say, suppose we have a sub basis for this by. Okay. Suppose sy is a sub basis for this by. So if sy is a sub basis for this by, then every basis element, if I consider, then every basis element b from by, it's a finite intersection of the elements from sy, right? That b is the is some intersection of elements, say I is equals to 1 to n sy. Sorry, I is equals to 1 to n, let's say si, such that each si is in sy. Right? But then what is f inverse b? Okay, what is f inverse b? So f inverse b is basically intersection over I is equals to 1 to n f inverse si. Now we know that finite intersection of open sets is open, right? Finite intersection of open sets is open. Therefore, if F inverse Si is open, right, then the finite intersection of each of these F inverse Si is also open, right? But that implies F inverse B is open. Therefore, therefore, if so, I guess it's obvious from now that if tau is a topology generated by a basis B having a subbasis say S, it's enough. Sorry, if just claim it like this: if F from X to Y is a mapping with tau Y being the topology on Y generated by a basis By having a subbasis Sy, it's enough to show inverse image of each subbasis element is open to show F is continuous, right? Because if each subbasis element is open, then each basis element becomes open. If each basis element is open, sorry, if the inverse image of each subbasis element is open, then the inverse image of the basis element is open. If the inverse image of a basis element is open, then the inverse image of every open set is open, and that implies F is a continuous map, right? Clear? Obviously, subbasis elements are much smaller a structure than the complete topology, and will also be a simplified structure because the elements in the subbasis, since they are being used to construct the whole topological space, so they as elements are very simple. So it would be very simple to find the inverse images, or rather to locate or to consider the elements of the subbasis than considering elements of the whole topological space. That's why these observations are pretty important. Okay, I guess it's clear. So an immediate definition which arises from the concept of uh, continuous functions is the concept of what a homeomorphism is. The every theorems and lemmas related to continuous functions we will be studying in the next lecture on continuous functions. What is a homeomorphism? So f from x to y is said to be a homeomorphism provided x and y are topological spaces. Provided x and y are topological spaces. If f is continuous, bijective, and f inverse is continuous as well, and f inverse is continuous. Okay, in this case we say x and y are homeomorphic. In this case we say x and y are homeomorphic. Now observe these statements carefully. Previously we had claimed this, that, or rather we had seen this, that the concept of a continuous function is completely dependent on open sets. Okay, let me just write it in language. The concept of continuous functions is completely dependent on the topology. on the topological structure of the domain and codomain. Or rather, let me just be very precisely say that it's completely dependent on the open sets. Let me be very specific. Dependent on open sets. Okay, open sets. Therefore, if f from x to y is a homeomorphism, doesn't it readily imply that x and y have the same topological structure? This implies x and y has similar topological structure. Why is it so? Let me be very, just saying this, because observe that if f from x to y is a homeomorphism, then we have seen that f and f inverse both are continuous. So doesn't that imply that f from x to y is a homeomorphism if f of u is open, if and only if u is open, right? Surely f of u is an element of y and u is an element of x. Therefore, the open sets in y are completely determined by the open sets in x, and vice versa. That open sets in x are determined by the open sets in y. Therefore, the x and y are having similar topological structure, because what is the topological structure specifically? It's the collection of open sets. So topological structure is completely determined by open sets. We can completely determine the open sets of y with respect to the open sets of x and vice versa. Therefore, x and y are having same topological structure, right? So if f from x to y is a homeomorphism, then x and y are having same topological structure. To be a bit relevant to this, we have studied abstract and linear algebra, right? There we had studied certain functions which induce similar structured sets. Like for example, when we have groups, then we have something called an isomorphism. So it was a mapping. So recall that if G and G star are groups, then f from G to G star is called an isomorphism if G and G star have the same, if G and G star have the same group structure, right? Similarly, in case of rings, they are having same ring structure. In case of fields, they are having the same field structure. In case of vector spaces, they are having the same vector space structure. In this case, they are having the same topological structure. So therefore, a homeomorphism is exactly similar to what isomorphisms are in case of algebras. Here we have the concept of a homeomorphism, to be very specific. So two topological spaces are homeomorphic. One condition is there exists a bijective continuous mapping such that its inverse is also continuous. And the other trivial observation or conclusion which we can draw is that they are having the same topological structure. Then we can say that they are homeomorphic. Clear? So let this lecture be up to this much. In the next lecture, we will be talking in details about the theorems related to homeomorphisms, to continuous functions. We will be also talking about how to construct continuous functions from some given ones. Okay. So meet you guys in the next lecture.